So we're going to start things off here looking at the representation, or rather representations, there's more than one of them, on homomorphism modules. So we're going to let G1 and G2 be Lie algebras over K. Let each MI be a G module. UI, the enveloping algebra, of each GI with a map sigma I from GI into UI. With this, we have each MI as a left UI module and hence L, the linear maps, and K linear from module M1 to M2 has a canonical left U1 inverse tensor U2 module structure. So now this U1 opposite tensor U2 is the enveloping algebra of our G1 opposite times G2, and the mapping sending each x1 comma x2 into sigma 1 x1 tensor 1 plus 1 tensor sigma 2 x2. This is the canonical map of G1 opposite times G2 into U1 opposite tensor U2. Hence, there exists, we can reduce our module structure down to G1 opposite times G2 I think this table's loose. I don't think I can do anything about it in this video. Sorry about that. And this is, we can get this new structure on what we're going to call M, which is going to be our LK M1 to M2 as a module. And this is going to occur such that the bracket of x1 and x1 comma x2 inside of M acting on U. And this is going to give us a new map, right? Because so x1 and x2 is inside G1 opposite times G2, and it turns a map U from M into a different map U of M, which that map can then act on an element of M1, turning it into an element of M2. And the way it does that is equal to sigma 1 x1 tensor 1 plus 1 tensor sigma 2 x2. This is going to act on U, which is itself going to act on M1. And that reduces down to just being just equivalent to U of x1 in M1 acting on an element of M1 plus element x2 in the context of M2 acting on U of M1. This defines a representation of G1 opposite by G2 on M. Now, in our diagonal case, where G1 is equal to G2, which we're just going to call G, then the homomorphism, which, keep in mind, it's the diagonal map where the left side is the opposite, so it's going to send it to negative x comma x, or G into G opposite times G. Of course, this is then going to act with the above representation defines a representation of G on M, and so a G module structure of M, and does that by x in the context of M acting on a element U, then acting on an element of M1 is the component of x in M2, acting on U of M1 minus U acting on x of M1 acting on M1. We can write this more directly as xm acting on U is xm2 acting on U composed with U minus U composed with xm1. With with our results from the tensor representations. We get, here's a proposition which we get from our current results. I'm going to let G be a Lie algebra over K. And we're going to let mi indexed from 1 to n plus 1 be G modules. We're going to let n be the K module of Lk of m1 through mn on mn plus 1. There exists a unique G module structure on this n, which is this linear thing, such that x to the n acting on u, then acting on a vector of n components. I guess it's more of a list than a vector. It's equal to minus the sum of u of m1 up to xmi acting on mi up through mn plus x to the m plus xm to the n plus 1 acting on u of our vector of m1 through mn. And we get this through the previous result with a, I believe m1 through mn is just like the whole tensor deal that we saw earlier. So now let G be a Lie algebra over K. Let M be a G module and K a trivial G module, which I believe means the is given by the zero representation, which I believe means that the scalar product of, I guess, the kind of like the Lie algebra product of elements of G on elements of K is just always going to give you 0. Then from the previous proposition, we have a G-module structure on the k-linear maps from M to K, which is the dual space of M. And the corresponding representation is called the dual representation of our representation x to x as an operator over M. And we have we have x of M star acting on a function f, a linear function f of M, to give us the negative of the action of f of the action of our original xm on M, for of course f is a linear function on M, M is an element of M, and x is in our group. So this gives us that x as a representation of M star is just equal to, I believe that is the negative of the transpose of x. I'm not exactly sure about the notation there. They just have like a lowercase t vaguely close to x, but I don't see how else it could be interpreted. And this is how I learned to write the transpose, so hopefully that is the right formula. And so when K is a field, and M is finite dimensional, the G module M is simple or semi-simple. If and only if the fm star as a G module is. Okay, proposition. Let M1 and M2 be two G modules. The canonical K-linear mappings we have one from the dual of M star tensor, that's the K tensor of M2. I guess we'll call this map phi, to the K linear maps of M1 into M2. And psi is a K linear map from M1 into M2 star is being sent to the dual of the K tensor of M1 and M2. And it says this one is bijective. These are G-module homomorphisms. So I don't know what these maps are explicitly because I don't have the text in front of me that it's referencing. But I would reckon to guess that phi, because so the elements of phi are generated by linear maps, by dual maps of M1 tensor elements, an element of M2. So I'd guess that it sends okay. If you have F in M1 star and M2 in M2, I would guess that phi of F star, no, phi of F tensor M, I'm gonna abandon this too. And keep in mind, these are my guesses, these are not the canonical formulas. Would probably be this is going to act on element X. It's probably going to get sent to f of X times M2. Because like it has to be linear with respect to F. F is being sent to like a member of a linear map, so that seems like you get what I'm trying to get at, right? And then if you have here an element F sending element of F M1 to M2, this is going to be a map. This is going to act on F. Just going to send it to a linear function, to the dual space of that M1 tensor M2. Well, F of M1. F is an LK of M1 to M2 star. So F of M1 is going to be a linear function M2 star. So I guess it would look like this. Keep in mind this first one, this is multiplication. The second one is repeated evaluation. And once again, I'm going to stress these are guesses. These are the most obvious maps for these two linear functions, but I don't actually know for sure. So, watch out. And we're going to write for shorthand for our proof. we're going to write phi as being from n to p, and psi as being from q to r. Now, let's look at our proof. So we're going to let x and g f in m1 star, and of course m1 in m1, m2 in m2. Then phi of xn, so xn is x as a linear function on m1 star tensor m2, and this is going to send us to a different xn acting on our space n, members of which look like f tensor m2. So this gives us, so this is composition on the left, so so I gotta figure out exactly how to evaluate this. This is of course going to get, so f tensor m2 is an element in n, that is m1 star tensor m2. xn is an element in the is a representation acting on it, so it's in the homomorphisms of that, so it's going to send it to a different element in m1 star tensor m2. Phi is going to then send that element in n to an element of p, which is a linear map from m1 to m2, which then acts on an element f, m1. And so how do we evaluate that? Well, this gives us phi of x m1 star, which is the left element. Keep in mind how it splits across tensors. 2 plus f times its restriction, its version in m2, acting on this component m2. And this whole thing is still acting on m1, which is equal to angle brackets, that's the inner product, so that's the equivalent to, I'm guessing, the evaluation of a function in the star of a space with an element in that space. So yeah, and I was right, it is x m1 star f, the inner product with m1 acting on m2, and plus the inner product of f with m1, then acting on, composed with x, m2, acting on m2. Now, how does this work the other way? xp of phi, composed with phi of f tensor m2, this whole thing acting on m1. And the way I'm interpreting this does seem to be, if I'm reading it right, this is the formula I gave above, which is a good sign. So that looks like a 2 in the subscript. This is x in M2 of phi of f tensor M2 acting on M1 minus phi of x of f tensor M2 acting on xm1 of M1. So this is, yeah. And then this is equal to, on the left, the inner product of f m1 of x to the m2 minus the inner product of f and x m1 times m2. And if you look at this, this actually does end up lining up with the formulations we have above. This is m1 comma, no, that's not where the comma is. Because this here, yeah, one of the elements is the same, the other we're swapping over the place of x m1 with its star, which gives us a minus sign. And so phi of x n is equal to xp of phi. So that's our first one. And for our second case, for x and g, u in the linear maps from M1 to linear maps of M2 star, well, I guess the dual map of M2, dual set. And we have M1 in M1, M2 in M2. Then we have C of xq acting on u of m1 tensor m2. This is equal to, what did I think phi was equal to? Oh yeah, okay. Well, this gives us it as xq composed with u acting on m1, then the inner product with m2, which is equal to the inner product of x in the dual space of m2 star acting on, composed with u acting on m1 minus u x m1 of m1, and that's the inner product with m2, and so x to the r phi of u of m1 tensor m2 the phi is sending the map to the dual space of M1 tensor M2. The phi sending U to the dual space of M1 tensor M2. So then we have this element in M1 tensor M2. And so we have U, which is getting represented on by an element X, and then sent to the dual space of the element on the right in some order. And yeah, we get this one as negative the inner product of C of U and then X inside M1 of M1 tensor M2 plus M1 tensor X of M2 acting on M2, which is equal to negative UX M1 of M1 with M2 minus the bracket of U M1 X M2 M2. And so CXQ equals XRC, and we are done. Because we have the top equals the bottom essentially by linearity. We've got to move this XM2 over to the other side, which changes the sign, but otherwise, yeah, everything makes sense there. Now, the G modules L of M1 on M2 L2 M2 star and M1 tensor M2 star are identified under C, which is an isomorphism. So if M1 and M2 have finite bases, then our first map phi is also an isomorphism. And this identifies the dual of M1 tensor M2 and the linear maps from M1 into M2. In that case, we can therefore identify L, how am I going to write this? Identify M1 star tensor M2 star through phi as being congruent, equivalent, isomorphic to L of M1 and M2 star, which by C is then isomorphic to M1 tensor M2 star. So the dual space star kind of splits over the tensor product. I don't know if splits is the right term. And while this is a little short for a video, that's the end of this section, and I feel like I should scan through the next section before we go through it. And so we're going to actually call it here. Maybe a bit of a shorter one,